In the meantime, we have super interesting panels and keynote speakers coming along. Our next one is a chemical engineer and a visionary team leader passionate about creating value from new ideas. He's a devoted entrepreneur with experience of building VC-funded technology startups from first idea to multinational operations. Please, guys, okay, just live in silence. He's wait here, wait. He is here as the CEO of Core Power Ocean, a Swedish wave energy developer, bringing a threefold improvement on the efficiency of harvesting wave energy. Doesn't it sound like an absolutely fascinating subject? Well, let's hear directly from him. Please welcome Patrick Möller. Welcome, Patrick. Go there. Do you need
the clicker?
Sure. Thank you, Patrick.
Thanks a lot for that. My name is Patrick Möller. I am the CEO of Core Power Ocean. We are a wave energy developer based out of Stockholm, working closely with Kick Energy and Iberdrola here in Spain. So today I wanted to take the next 15 minutes and give you a little update on the state of the wave energy sector and comment on a few of the key challenges still remaining in this highly interesting opportunity of making commercial harvesting of energy from our oceans. Starting with that, you can say wave power is an extremely exciting opportunity. It is a very significant resource of untapped clean energy, and it's the most concentrated form of any of the renewable energy sources. We're speaking about something like 10 times more energy density than solar and 5 times more than wind. So it should be possible with a fairly small device to extract a large amount of energy. And it's also very predictable. You know a few days in advance exactly what's coming in. So it's not like the wind or the sun where you suddenly have a cloud or you have a change in the wind. You know exactly what's coming in for the next 2 to 3 days. And because of that, when we are going to grids with 100% renewables in the next years, as we're seeing COP21 agreements being put in place, and we're really going towards tackling climate change, in order to get the high percentage of renewables into our grids, we need a stable combination of sources. And there, wave power can be seen much closer to something like a base load compared to other more intermittent energy sources. It's also local generation close to our coasts. We got something like 40% of the global population living near the coasts, and that's where you can extract the best sources of energy here. Somewhere around 10 to 20% of the global electricity need could be satisfied by wave energy if there is a reliable, a cost-effective solution found. So you get all the physical properties there, the opportunity is huge. Why don't we still see any real contribution to our grids from wave energy? The real challenge here is to design a device which is robust enough to survive the toughest storms, at the same time generate enough energy to make it a commercial business. And in order to survive the storms, so far, wave energy converters have been forced to be so large, so heavy, and thereby too expensive to make it a viable business case. If you look at some of the most important metrics, for instance, how much energy you can generate over a year compared to the amount of material, the tons of equipment you need to put out there to do it. It's very interesting. There's been a lot of attempts in wave power so far, all different kinds of buoys oscillating up and down in the surface. You get attenuators like big sausages moving up and down. You get flaps moving to the sides. But a common thing for all devices so far is that it has been hard to get more than 1 to 1.5 megawatt hour per ton out of them. If you look at a modern wind turbine today, it's just above 10 megawatt hours per ton. And when we started this project about 6-7 years ago, we realized that we need to do something dramatic about this if we're going to be able to make wave power successful. And that is what we have been proven so far. So Core Power Ocean, together with our European partners, have proven a compact, high-efficiency wave energy converter inspired by the pumping principles of the human heart. And we use a technology called phase control to get these buoys to oscillate in resonance with each incoming wave. And this strongly amplifies the motion of the device and thereby the power capture. And this allows a large amount of energy to be harvested using a small, compact, and low-cost device. Such low-cost and small devices are easy to handle, they're easy to transport, and we've also been able to develop very low-cost effective operations and maintenance methods. Together it comes down to really tackling the cost of energy in order to make waves as competitive as wind is today. If we're looking at this device, the first thing to make it competitive is to make sure that it survives the storms. We do that with the technology making it too fast for the incoming waves. And then we make it move in phase when the waves come in. And what you see here is when we have phase control on, the device moves significantly higher than any of the incoming buoys. Well, that's me. And the unique thing is that we can combine a device which is not excited by the waves in the storms, and when the regular waves come in, we get in average 3 times as much energy for the same size of the buoy. We switch to the next. The data we have proven so far has shown that compared to the state of the art, we've been able to extract 3 times as much energy per force, which is a good measure of the cost of the drivetrain situated in these wave energy converters. And we've been able to get more than 5 times as much energy per ton. You remember the number 1.5 megawatt hours per ton, which has been the state of the art until this point. We're now showing a path for the wave sector to get above 10 megawatt hours per ton, so more than 5 times as much. And by that, we're giving the sector a path to match the structural efficiency of a modern wind turbine. And we've been able to do that in just a few years now. And if you're looking at the equivalent in wind, the state where wave power has been is somewhere comparable to the 1980s of wind turbines, where both if you speak about structural efficiency and the cost of energy, it's taken about 30 years of continuous improvements to get wind to the level it is today, being one of the most competitive sources of energy. And we're showing now that we can do the same with just a few years of testing of these devices. And I would say it's all thanks to the concentrated nature of the resource itself, the ocean waves. And by that, we're aiming to show a cost of energy with wave energy that can compete with offshore wind just in the next years to come. Taking this complex technology to market in such a harsh environment as the oceans are, it's important to have a very structured approach. And we have tried to incorporate all of the possible learnings that we can from previous projects that have been done around Europe. And we have followed a 5-stage product verification plan, where we started in small scale, like 1 to 30 scale prototypes that we tested in Portugal. We've gone larger to 1 to 16 in our stage 1 experiments. We got very good data, and because of that, we could fund the next stage, where we did testing on 1 to 16 in France. And we built out our larger scale drivetrain testing. And currently, we're now piloting our half-scale devices with Iberdrola and a range of European partners. Assuming we're successful mid-next year with that, we then go into full scale in 1920, and in the 2021 timeframe, we expect to install the first larger scale arrays of these buoys that will generate electricity to the European grids. But this structured approach, I think, is one of the key things, and it makes us a bit different compared to what has been done in most other wave projects in the past. I'll show you a few of the examples. We've been developing gearbox technologies from the very start. In order to make it this competitive, it's a quite innovative type of solutions that we have had to develop. So completely new types of drivetrains have been developed together with leading automotive partners. And we've also built out a hardware-in-the-loop test rig where we can actually run all the drivetrains with simulated waves. And for the last 2 years, this drivetrain has been converting mechanical movement up and down into grid-quality electricity and shipped that onto the Swedish grid. And by this approach, we've been able to really tune the device, the control system, and most importantly, debug all the different functions and make sure that it's really reliable when we put it out in the ocean. In parallel with the mechanical testing, we've been conducted numerous runs of hydrodynamic testing, the most recent one at the École Centrale in Nantes, where we were able to run some 250 different experiments up to the equivalent of 32-meter waves, the biggest storms you will ever see in the ocean. We could tune the control system and really prove the numbers step by step that we have shown so far. Because of these results, we're now working with some of the, I would say, the best brains in this field all around Europe, and we are extremely fortunate to combine the experience in offshore wind and operations from Iberdrola Engineering that we're now piloting with the best researchers in wave from Portugal, in the WaveEC, working out of Lisbon. We're working with EMEC on Orkney, the test site in Europe that have tested more wave energy devices than anybody else so far, and the University of Edinburgh, who are the world leaders in cost of energy modeling in this field. And we've also had some real kick-ass innovation coming through some of the university groups, especially NTNU in Trondheim, who've studied these hydrodynamics for the last 30 years. The reason why we can get so much more energy out with a small device, it's very simple, reliable technology, but there's really 30 years of research in hydrodynamics behind it. Recently, we've gotten a broad support all through Europe for really proving this in a larger scale. We're funded by Wave Energy Scotland, Kikino Energy, and the Swedish Energy Agency here. We're currently in our stage 3 pilot together with Iberdrola, and we're doing that in 2 phases. Again, we're doing a huge dry test rig, where we are right now working with the device, tuning it and debugging it to make it as stable as possible before we're going to go into the ocean on Orkney up in Scotland in the April timeframe. The buoy has been manufactured in Portugal. It's currently in shipping on its way on a boat to Sweden as we're speaking right now. It's arriving next week, and then we will work with it under dry testing until April. Then it's going to be installed up on the EMEC test site on the Orkney Islands, north of Scotland, that has some of the most suitable wave climate for these type of tests. It also has a very long experience of what to do and not to do with these type of devices. And in the project, we are trying to prove this technology, prove that we get 5 times as much energy per ton, 3 times as much energy per force, but we're also trying to prove our business model, where Core Power as a startup has a very narrow focus of developing and supplying the world's most effective wave energy converter itself. But when it comes to installation, maintenance, the whole project development, we're working with established infrastructure companies such as Iberdrola Engineering, in this case, who take the responsibility for how to moor these systems in the ocean, how to connect it up to the grid with the electrical connection system, and how to service them. And together with well-established infrastructure partners, we're able to offer a turnkey solution to energy companies around Europe and the rest of the world. And by really bringing the best experiences from all previous projects that has been in this field around Europe, because Europe really is the leader in this sector today. There's more experience and more work than in any other place. We're hoping to prove that Wired is right by saying that we are bringing a sea change to this sector. And we're also hoping to prove that wave energy in itself, with its very concentrated nature, its very vast opportunity, will become the most competitive source of clean and renewable energy to power our grids here in the next coming 10 to 20 years. Thank you.
Thank you very much, Patrick. That was spotless on time. The good news is that Patrick is coming back. He goes, but he'll be back. So off you go. I'm going to introduce the next panel, and he'll be back. So in case there are any questions, right?